AB Calculus 3.6, day number 1, derivatives as rates of change. Today's objectives in this video are to talk position, velocity, considering the average velocity, instantaneous velocity, as well as speed, which is the absolute value of velocity. Some acceleration work. We're going to set up some word problems a little bit with instantaneous rate of change, and then what's called motion along a line, also known as particle motion. So let's start with taking the derivative of each of the 6 trig functions. You can pause the video and attempt these and then let it go and see how you did. So I'm going to continue. The derivative of sine is cosine. Derivative of cosine, negative sine. Derivative of tangent, secant squared. Derivative of cosecant is negative cosecant x cotangent x. Secant x is secant x tangent x. Derivative of cotangent is negative cosecant squared x. Just a reminder, check it out. If the function starts with a c, its derivative is the opposite sign of what it was. Okay, if your function is sine, tangent, secant, then your derivative is the same sign as the original function. Okay, let's get into this a little bit. We got class opener down here. Let's take a look at that. So it says, what is an instantaneous rate of change for a function? Well, it's the limit of the average rate of change as one x value approaches the other. So the two forms that we're most used to seeing, instantaneous rate of change of a function, let's say at x equals a, is considered f prime at a. So f prime at a can be written in two ways. It can be the limit as h approaches 0 of f of a plus h minus f of a over h, or similarly, the limit as x approaches a of f of x minus f of a over x minus a. Those are our two formulas using limits for the instantaneous rate of change of f with respect to x at a, also known as the derivative at a for f of x. All right, let's talk about motion along a line. We got to talk some vocabulary and some symbols along here. So the definition, instantaneous and average velocity. So let's say s, which is the position function, is equal to f of t, the position along the x-axis as a function of time. The displacement of the object over a time interval from t to t plus delta t, so delta t is just the change in time, is given by this. Delta s, change in position, is f of t plus delta t minus f of t. That's the same thing as the, let's say, the change in y. So the change in y was y of x plus h minus y of x, or f of x plus h minus f of x. When we wanted the average velocity or the average rate of change, what did we do? We took that divided by delta x. So we divided that by delta x. In this scenario, we're talking with respect to time, so we divide by delta t. That's the change in time over that interval. So the average velocity then is given by the displacement over the amount of time over that interval. The instantaneous velocity, very similarly to our definitions of the derivative above, are going to be the limit as the change in time goes to 0. That's no different than the limit as h goes to 0 of f of a plus h minus f of a over h, where this is now just the instantaneous change in position over time, okay, or the instantaneous velocity. So let's talk some details about velocity, because velocity has direction. Okay, speed has no direction, but velocity does. How do you know when the particle is moving to the left? Let's say the particle is moving horizontally only, no vertical movement at all. So if v of t, which is equal to s prime of t, if v of t is less than 0, that means the particle is moving to the left. If v of t is greater than 0, that means it's moving to the right. And the particle is at rest or stopped when v of t is equal to 0. All right, let's talk a little bit about speed here. We mentioned that speed has no direction. So speed is the absolute value of velocity. As you can see here, the absolute value of v of t is the same as the absolute value of the change in position over the change in time. So v of t is the same as we said s prime of t. Another symbol that we can use, or set of symbols to represent v of t, is ds dt, which is the change in position over time. So of course, like we got here, speed is the absolute value of any of those. Okay, the definition of acceleration is the change in the velocity. So with that being said, I do want to say one other thing, that acceleration is the concavity or second derivative of the position function. Okay, so speeding up and slowing down. I'm not going to go into the details, but a function is speeding up, or excuse me, a particle is speeding up if v of t and a of t have the same sign. Okay, so either both positive or both negative. All right, a particle would be slowing down if they had opposite signs. Okay, opposite signs. All right, so the summary of this last section: given position of a particle or object, the velocity is the first derivative of s of t, or s prime of t. Acceleration is the second derivative of s of t, or s double prime of t. Let's apply this to an example here. So example number 1, an object is traveling along a line with a position given by s equal t squared minus 2t plus 1. Let t equal 0 be the starting point. So let's first find s of 0. So the initial position of the particle, if I plug in a 0, I get out a 1. Okay, so let's find the velocity and the acceleration for the particle. It doesn't say at a specific time, so we're going to assume generally speaking. So s prime of t will equal, using the power rule, 2t minus 2. Therefore, v of t is equal to 2t minus 2. All right, now let's look at v prime of t. V prime of t will be the derivative of 2t minus 2, which is 2. Therefore, a of t is equal to 2. Now, what I do want you to do is define v of t as s prime of t. And then I want you to define a of t as s double prime of t. All right, so with that, what you've done is you've linked position, velocity, and acceleration. Okay, so we've found both the acceleration here in red, which looks like it's constant, which will be cool. I don't know why that's cool, but it'll be easy to work with. Okay, in part B, it says, when is the velocity 0? Well, let's set v of t equal to 0. And it looks like at t equals 1, v of t equals 0. So v of 1 equals 0. That means at t equals 1, the particle is at rest or stopped. Okay. C, when is the object moving to the left, moving to the right, and how do you know? All right, so the object moves to the left when v of t is less than 0, moves to the right when v of t is greater than 0. So let's sketch v of t. And here's, let's call this the v of t axis. And this would be where t equals 0. And we'll go out, I don't know, we'll go out maybe to 5 and we'll see what happens here. All right, so I'm going to sketch v of t. V of t is 2t minus 1. So v of t is 2t, minus 2. All right, so that's a linear function. And we know that v of t equals 0 at 1. So 1 comma 0. And it's a linear function. The linear function's y-intercept is 0, negative 2. Therefore, v of t should look like that. It says, when is the object moving to the left? Well, the object will be moving to the left. All right, it'll be moving to the left on this interval here because v of t is less than 0. So we would say on the interval from 0 to 1, since v of t is less than 0 on that interval, the particle will be moving to the right on the interval where v of t is greater than 0. So it looks like there is no bound on a line. Therefore, from 1 to infinity, since v of t is greater than 0. So we've set up, I guess you could call it test lines to check for direction. What I could have done is plugged in a value like, let's say 2, and seen that v of 2 is positive, and plugged in maybe a half and seen that v of 1/2 is negative. Okay, and since v of 1 is 0 right here, then we know that it's changing sign at that point. Okay, let's continue. Okay, part D is asking us to create a line graph of the motion of the particle. Okay, so here's what a line graph will look like. We'll just create a horizontal line. And what I'm going to do is actually create a table of values. So I'm going to plug in values for t and values for s of t, because the motion of the particle has to do with its position. Right? We want to find locations of where the particle is at what times. So we said that t of 0 was 1. And then, oh boy, I got to write down s of t here so I remember what I'm working with. T squared minus 2t plus 1. Okay, so we also know that v of t was 0 at 1. That means it's going to change direction, right? Because we saw that the velocity went from negative to positive at t equals 1. So that's a critical point for me so that I can see where that position ends up being. So I'm going to use t equals 1. If I plug in a 1, I actually get 0. And then I'm just going to, because I know that the velocity changes from negative to positive, the particle is going to head back toward the right. So let me resketch v of t here. We had 0, negative 2. We had 1, 0. And then we just had this line, right? So on this interval, I think I made it green, we said the particle is moving to the left. So between 0 and 1, the particle is moving to the left. And then after 1, the particle is moving to the right. Therefore, I can see that that point at 1, 0 will end up being the leftmost point on this motion graph, okay? So let's just pick a number greater than 1. Let's go 4. If I plug a 4 in, I get 16 minus 8, which is 8 plus 1, which is 9. So I get the point 49. And I know that the velocity will be positive, so it'll just continue to move to the right. So let's plot these points in order. So at time 0, the particle is at position 1. Okay, so this is a position graph, line graph that is. And then it comes back here to 0. Okay, so we start here. So at time 0, position 1. And then at time 1, it's at position 0. And then the particle starts to move back to the right forever. And at time 4, the position is 9. Okay, so based on our velocity graph, you can see that velocity is negative, negative, negative. Then it's 0 right here. And then since the velocity changes from negative to positive, that's a turning point in the line graph. And you can see the motion of the particle in that way. Okay, so let's analyze now parts E, F, G, and H. Is a particle ever speeding up? Well, speeding up has to do with acceleration and velocity being the same sign. So acceleration, we actually know, was the derivative of the velocity graph. And the derivative of the velocity is 2. So since acceleration is only positive, we're looking for where velocity is also positive. So v of t is greater than 0, we said, on the interval from 1 to infinity. Therefore, acceleration and velocity, a of t and v of t, are both the same sign same sign on the interval from 1 to infinity. So the particle's speeding up from 1 to infinity. Is the particle ever slowing down? Yes. We can see that they're opposite signs. A of t and v of t are opposite signs from 0 to 1. Okay, now what is the maximum speed on the interval from 0 to 4? Well, I'm going to look at the velocity. I see a velocity of -2, and then it approaches 0, and then it takes off. Now, it does say from 0 to 4. So what would the velocity be at 4? Because I'm guessing, what would that be? Because that will probably be our fastest speed, or our maximum speed. So v of 4 ends up equaling 8 minus 2, which is 6. So our velocity here is -2, but our speed here is 2. So from 0 to 4, our maximum speed would be at time t equals 4. So since our velocity at time t equals 4 is 6, our maximum speed is 6, I don't know, units per unit of time. Units per unit of time. I don't know, we don't have time on here in seconds or whatever it might be. All right, what is the total distance traveled from 0 to 4 on the time interval 0 to 4? Okay, so looks like I chose wisely with time 4 on my line graph. This is actually a pretty nice time to bring this up, but the total distance traveled was 1 to the left and then 9 to the right. So total distance is 10 units, right? But what is the displacement for you physics students out there? Displacement, you know what that is. For those of you who don't know what displacement is, it's just the change in position. So the displacement here is from start, I'm going to change my color here. Let's go purple. From start to finish here in purple, the displacement or the change in position is only 8 units. Okay, so the difference between total distance and displacement in this case is 2 units because, well, the particle went to the left 1 unit and then had to recover that same amount. Okay, let's continue with the next slide. Okay, we're going to look at some FRQ work here. So let me go ahead and get my pen ready here. AP problem from 1999, back in the day. It says a particle moves along the y-axis with the velocity v of t equals t times sine t squared. Okay, so once you see that, you should be fairly confident that it's going to be a calculator allowed problem. You can see that that's true for t greater than or equal to 0. In which direction, up or down, is the particle moving? So what I want is I want to know v prime, I want to know v of 1.5. Okay, so easier said than done. What I'm going to do is I'm going to plug v of t in for y1 in my calculator. Okay, so I get that plugged in. Make sure you're in radian mode. Radians. Okay, and then what you want to do is go back to your home screen and press alpha. Okay, and then trace. And then select y1. Okay, so up on your screen you should see y1, and then put a parenthesis and type in 1.5. So that's plugging 1.5 into your velocity function. All right, you get 1.167, and therefore you can tell that the particle is then moving. Now instead of left and right, we're going to be moving either up or down. So it'll be moving upward since v of 1.5 is greater than 0. Okay, now let's look at part B. Part B says find the acceleration of the particle at time t equals 1. So I want v prime, or 1.5. I want v prime of 1.5, which is equal to acceleration at 1.5. Now how we do that is you're going to press the math button, and then 8, and then up on your screen, this should pop up if you have a newer calculator. Something that looks a little bit like this. All right, and then all this good stuff. Okay, so you want to put x here because we're differentiating with respect to x, or actually, well, yeah, your function goes in as x times sine of x squared. Okay, but it's an easy transition between variables. Okay, and then the exact same thing we did right here for alpha trace y1, do that to select y1 here. So we're going to be taking the derivative of y1, which is the derivative of velocity, which is acceleration. And when you had picked this red x here, it will autofill that red x there. And then of course I want to plug in 1.5. And this will calculate the acceleration at t equals 1.5. So that value comes out to be, let me see here. If I round to 3 decimals, comes out to be negative 2.049. Question is asking, is the velocity of the particle increasing? Why or why not? And we would say that the velocity, right, is decreasing Okay, it's not asking about the speed increasing or decreasing, so I'm not worried about the signs of velocity and acceleration. The velocity is decreasing because v prime at 1.5 is equal to negative 2.049. So think about that logically. I want to know where f is increasing. Well, f is increasing when f prime is greater than 0. Therefore, v is increasing when v prime is greater than 0. In this case, v prime is less than 0, therefore velocity is decreasing. Okay, AP problem from 2003, calculator allowed again. First thing that you want to do, as usual, calculator allowed problem is type v of t in for y1. Okay, and then let's note, I don't know if we'll need to use it, but let's note this comment right here, which tells us that x of 0, or the position, in this case, we're used to seeing position as s of 0, but they're using the letter x, so use it. The position at time 0 is 1. It says in part A, find the acceleration of the particle at time t equals 2. Is the speed of the particle increasing at t equals 2? Why or why not? So not only do I need to find the acceleration at time 2, but I need to find the velocity at time 2. So v of 2, I can simply use the same thing I did up at the top, alpha trace, y1, and plug in 2, and hit enter. It looks like I get negative 2.728 rounded. Therefore, v of 2 is negative 2.728. Okay, v prime at 2, which is equal to a of 2, using my calculator, the derivative with respect to x of y1 at x equals 2 comes out to be 1.588. So a of 2 equals 1.588. It asks, is the particle increasing, or the speed of the particle increasing? We can say no, it is not speeding up. Not speeding up, since v of 2 and a of 2 are opposite signs. Okay, on to part B. It says find all times t in the open interval from 0 to 3 when the particle changes direction. Justify your answer. Okay, there will be a change in direction when the velocity graph is equal to 0 and changes sign. So in y1, we already have our velocity function. So we want to graph it. We want to know on the interval from 0 to 3. So how I would set my window if I were you is my x min would be 0, my x max would be 3, or maybe a little bit over. And then my y min, I would probably go negative 1 up to positive 1, because all I really care about is the function crossing the t-axis. So when I graph it, my graph of v of t looks kind of like this, okay? So I want to know right here what this point is, because the velocity is going from negative to positive, which means it's going to change direction, which means from 0 to whatever that t value is at the blue point, the particle will be moving to the left, and then at that time it pauses and then starts moving to the right. So when I use my calculator, what I'm going to do is, okay, to calculate this point of intersection with the x-axis right here, I want you to go through the following keystrokes. Okay, when you're on your graph, I want you to press second, and then trace, and then go to 0. Okay, 0 will be your option. What it will do, it'll prompt you. You'll be along the curve somewhere with your cursor. I want you to take your cursor, it'll ask you for a left bound. So it'll ask you for a left bound, put it anywhere to the left of this point. Okay, press enter. And then it'll ask for a right bound, so then you scroll over to the right of that 0, press enter, and then it'll say guess. And you don't need to make a guess, you just press enter again, and then that'll give you your value. And what I end up getting is the point t equals 2.507. So I know that the particle changes direction at t equals 2.507. So we have a change. Let's write a description. In direction at t equals 2.507. And the reason we know that, other than based on the graph, is that v at 2.507 is equal to 0, and v of t changes sign. All right, there you have it. I think we've got one more example. Let's go to the next slide. All right, quick little example here. 2008, a particle moves along a straight line with velocity given there. Again, first thing you should do is type that into your calculator as y1. Okay, so y1 equals that function at time t greater than or equal to 0. What is the acceleration of the particle at time t equals 3? So math 8 brings this up. Plug in an x, plug in y1 using alpha trace y1, and then at x equals 3. And what that will give us is 0.055. Always round to 3 decimal places. And there you have it. That's it for today's lesson. We'll see you in the next video.